Welcome back again. So we will start with the next session. I'll start sharing my presentation. Now I think it is visible to you all. Yes, thank you. So the topic for this session is low carbon materials. So we have been listening about the low carbon materials since the day one. And we have been talking about the EPDs the material should have, how to calculate them, from where they come, how we use them in WLCA, etc. What exactly low carbon materials are. So in this particular session, I'm not going to suggest any low carbon materials. The basic reason is that since the start, we are looking into the details and we understand that the low carbon potential of a material changes with different variables. There are n number of variables and the potential will change. So what we will have in this particular session is how we can design the low carbon materials, what are the some basic examples of those low carbon materials we can have, and if I have 2 or 3 options for a particular low carbon material for my own project, which particular material should I choose? So I will discuss one method for that choosing low carbon material for a project. So we'll start with the basics. We have been listening to the word GWP. I hope you know the definition, but I'll just reiterate it because there are 2 terminologies we have been using. One is the GWP and another one is the low carbon material. So in all one-to-one, we can use them. Alternatively is global warming potential is the warming effect of a certain amount of greenhouse gas over a set period of time, usually 100 years in comparison to CO2. For example, if the methane's effect on climate is 28 times more severe and 100-year GWP of methane is 25, then I will say that the carbon footprint measured in kilogram carbon dioxide equivalent, it will be 25 tons. So if I am saying it is a low carbon material, essentially I should say it is a CO2 equivalent for that particular material that I have to calculate. So then I will say that yes, it is GWP, which is just now we have seen the EC3 tool. So it is giving us the GWP. Why we are concerned about, so I will be basically taking the scenario in our country or in India. If you see the graph to the right side, it gives you the emission through 1950 to 2022. And you will be a little, you will feel a little difficulty to find India in this particular graph. Because if we see to the CO2 or equivalent emission through our country, that emission is low. Because still now we are not that much advanced in the automation in construction, or say the fuel which we are using in construction is not that much. Cannot claim this, but as this graph is showing us, the India has a very lower CO2 emission through time. You will find that after 1990, it has increased many folds. And we are right in the time to curb it. So whatever we are doing right now to curb CO2 emission. Is it now? Now,
Stop sharing once.
we'll try.
But now I will go full screen and then.
No, it will not work that way. So, sorry for this disturbance. So I was talking about that if you look into the India, the emissions are less as compared to the world's emission. But yes, we have started doing it right in the time. If we look into the sectoral GHG emission, we can find that IPPU, that is industrial processes and product units, it is quite high, 8%. And if you look into the energy, it is 76%. In IPPU, it is excluding the energy. So if we look into the energy, we know that construction is a very energy intensive process. So how this trend in construction material has changed and why now are we worried about the CO2 emission from the construction sector? If we look into the very first use of construction material, you will find to the left of the flow chart, it is availability. Start of the using material for habitats, whatever was available, it was used. It was a perishable material, basically the wood, so completely carbon neutral, we can say, as the definition suggests us. So yes, it was not having any carbon emission. On the other hand, it was carbon sequestering, but the durability of that particular material was a very big issue. And if you calculate it to a very long period, probably that material will not be a sustainable material from that point of view. So next came in the durability concept. We wanted our material to be durable. For the materials to be durable, we had to choose different raw materials. Basically, the earth-based material, we chose clay, we chose stone and timber, which required dressing as well, or processing as well. So two things came. First, the material which we are choosing, we are extracting it from the earth. Second, we are processing it to some particular degree. It increased the durability, but it added on the CO2 emission to the material. But we did not think of the CO2 emission we are not worried about that particular thing in this particular stage. Then came the synthetic material. We made some composites, two-part composites, like brick is also, you can say, a composite, different characteristics of constituent are, and when you are mixing them and you are making the brick. Concrete is also a composite, maybe a ceramic composite, alloys and polymer, differently in their own material family. It increased the durability of the habitat, but it added on, or it helped to stick that CO2 emission with the material development in the due course of time. Then we were worried about that habitats were expanding, our needs were expanding, and the simple durable material would not satisfy our needs, so we went into high strength composite. Now comes some concept of total low carbon emission through the material. If we are using a very high strength composite or high performance material, probably the quantum of the material you require will reduce. And if you calculate the CO2 emission associated to 1 unit, in total, probably it will be lesser than what conventional material will give us. This picture can be more clear if we do the whole life cycle assessment for both the materials. So then came the strength. For the strength, we required some high performance admixtures, polymers, high strength composite. We needed to design the materials differently. And then there were a variety of material coming, different family composite. For example, RCC, we say a ceramic and metal composite, or a carbon fiber reinforced concrete, or polymer, we say a polymer and metal or ceramic material composite. Then came, there are two types of carbon emission we have learned in 3 days: embodied carbon emission and operational carbon emission. So we were reducing the embodied carbon emission through changing the material or doing some permutation combination, but we were not looking into the operational carbon emission. So then came the concept of functional performance of the material. We wanted the composite, which gives us a durability, which gives us high strength, which gives us high performance. At the same time, it gives us a good function. Good function means it can help reducing the operational energy in the building envelope or say in infrastructure. Probably I'll be able to make that composite using less processing energy. So processing CO2 reduced. Probably I'll be used to make that material with locally available materials. So transportation energy reduced. Or probably I'll make that material help making my building envelope so thermally efficient that the operational energy of the building as a whole reduced. So the the intervention of this material in reducing the whole life cycle carbon comes into when we do that WLCA for a building and not for a material. Initially, the material may have a higher embodied energy, but when it comes to the operational energy, this will help in reducing the building operational energy. But then again, we were not satisfied. We wanted serial number 3, serial number 2, 3, 4, all in together. So we tried to develop, or all this development went up to the sustainable materials. So a sustainable material, by definition, you know, it should be available in my vicinity or locality. It should be durable, so I don't have to use much of the non-renewable resources of Mother Earth. It should have good strength, so it should be satisfying my need for a good structure. It should be good in functional performance, should be satisfying the occupancy and comfort. And essentially, it should have a low embodied energy and low embodied carbon. This is a very interesting periodic table, which I have taken from a publication from DAS, recently published. If you look into this, they have 7 columns and 8 rows. And the index shows us there are polymers, column 1 to column 6, and row 1 to 8. So look into column 1 to column 6. And row 1 to 8, you will find these are all polymer based material. Inorganic base may be there, organic base may be there. And you know there will be different synthesis energy required for inorganic. There will be different logic, or biogenic, as Sir was telling us, is the different logic for organic based polymers. Their performance will be different. So we can find some good materials which we are using right now in our construction industry. For example, PVC. Polyurethane. If you look into the orange, rightmost bottom is PVC, polyurethane, polystyrene, starch-based thermoplastic. These all material we are using either in form of insulation or fibers in making our construction material. Then there are biodegradables. There are elastomers. There are thermoplastic. Can be both thermoplastic and thermosetting. They can be thermosetting, and they can be only mineral-based material. So there are 3 classifications, or I can say the classification is according, materials are classified according to 3 things. One, you can say the color classification. In the polymers, you can say there are 4 colors. One is the blue color. It says they are elastomers. You have heard of elastomeric bearing, which we use in bridges, right? You must have heard of elastomeric sealant, which we are using in retrofitting repairing. Then the orange one, they are thermoplastics. So we use these thermoplastics in maybe packaging of construction materials. Then there are thermoplastic or thermosetting. For example, polystyrene we are using, or polyurethane we are using in the insulation material. And then there are thermosetting which are yellow. You can see epoxies and ionomer are there. Epoxies we are using for using as adhesive in construction material. So all these belong to construction material basically. And the pink one gives us the mineral based material which are more popular in our construction industry. So this is classification. What information does it give? If you look at the information, it is giving us the value of embodied energy. Embodied energy is shown in the left top corner, and value of global warming potential. These values you know now by 3-4 days discussion that these values are pertaining to the case study which these authors have done. So, but we can, how this periodic table is of our use. When we see that we are supposed to select a material for synthesizing a new low carbon material, I have to make a choice between different available options in the market. So if I have a choice between 4 blue material, which I say all the 4 blue materials are elastomer and I have to choose one, what I instantaneously see is the global warming potential of that material amongst the category blue. Similarly, if I go to the 7th column, the mineral based material, they are giving me different options, exclusive options, there is no choice. So in that particular option, I will have to do something to bring down that GWP or the embodied energy value of this particular material. Right? So isn't it interesting? Now this gives me one more insight that can I prepare the same periodic table for my own project? Because since the values shown by the author for which we are referring are their own, and my project will have a certain geographical location, will have a certain constraint by the standards which my country is applying to scenario. There will be some constraint of the material availability in my own region. So I may not have these many options. Probably my periodic table may be something different. And then naturally the embodied energy values and the GWP values for my own region will be completely different. It's a very simple example that if I want to do some flooring in a building, and if my geographical location is Maharashtra, there are not many flooring material available, so I have to bring them all together from, I mean, if I'm using tiles, it is okay. But if I'm using, say, marble, then the choice will be completely different. So can I prepare such a periodic table for my own project, which can help me in finding out different alternatives and then making a choice between or choosing between the whatever available materials are there. Okay, so let us move next this is another list which is given by CPWD Department Guideline 2014. They are saying that if you have energy intensity definition for a building material, so energy intensity, they have not given the GWP values or they have not given the CO2 values. But we know that if it is energy intensive material, naturally it will be either based on fuel, coal, diesel, electricity, whatever it is. It will change, but it will remain the same that if it is a fuel based or energy based material, high energy intensive material will naturally have high global warming potential, right? So they are saying that why very high energy intensive material greater than 50 gigajoule per ton, high energy material, medium energy material and low energy material. If you look at the table very carefully, it says that our material which we use in construction are in 3 lower categories. Because if you look into the aluminum, we are also using aluminum, but the quantum of aluminum which we are using, if you look into the BOQ, it is very less as compared to the other different materials. Look to the third and fourth row. You will find that the concrete is in the third row. So it is a medium energy material. And you will find the aggregate. May it be a fine or coarse aggregate. It is in the fourth row, which is a low energy material. So if I go to conventional concrete, I know that 60-70% aggregate I am using. So by nature, my concrete will be a low energy material. But as soon as cement comes into picture, because it is a high energy material in the second row, my concrete becomes a either high energy material or a medium energy material. So what is the takeaway from this table to me is, if I still want to keep my concrete in the low energy category or that particular classification, I have to replace cement. Right? So that gives me an idea that if I am going for a low carbon material, cement replacement is a very good and viable option to bring the total energy intensity of my own material. In turn, it will reduce the carbon emission or GWP of the material. Let us go beyond. So we are saying carbon emission or GWP. The carbon emission plus minus carbon reduction is if it is equals to 0, it is a zero carbon emission. Right? If it is positive and if it is negative, it is a carbon minus. I am not only offsetting the carbon emission which I am creating because of use of the construction material, but I am doing something additional which will offset that particular carbon emission and give the carbon sequestration. This comes with, I mean, this is not directly related to low carbon material, but as I said, the low carbon material, ultimately, if it is a functionally performing material, is going to reduce the operational energy. And to some extent, if we can reach to the threshold where the operational energy is reduced, we can move to carbon minus concept, right? I hope it is clear. So my agenda for low carbon material should not only be material embodied carbon reduction, but the material should be a good functional performing material. So to lower the operational energy of the material. That will be in, I mean, so there is a backup from the government action plans. It is National Action Plan on Climate Change, NABCC. Several climate change meetings and protocols over the globe. As I said, we have picked up early. We are very less carbon emitting country as compared to the global, if you see the statistics, but we have picked up early and we are doing good. So our National Action Plan, useful, these are 8 indicators. So out of these missions, 8 missions, so out of these missions, what is of our use is the National Mission for Sustainable Habitat. You can see the second one in the first row. And for enhanced energy efficiency, the fourth one in the first row. So these two, we as a construction industry professional, we can directly address if we take certain actions into. For National Mission for Sustainable Habitats, the thematic areas are energy and green building, urban planning, which Rajeshri Madam took yesterday, mobility or air quality or air pollution, water management and waste management. Still we are lagging a little behind in waste management. So there is not much of the data available as far as the construction industry waste is concerned. And there is no much happening for developing the materials through that construction waste. Okay, so now I want to push that low carbon material, I want to push the material into the circularity. So there will be certain indicators for circularity. Ultimately, I have to choose amongst the available one. The material is not going to come from somewhere which is not available. So I have to choose from the available one and I have to push it to the, say, circular economy. That is a very basic point, because ultimately everything will stop on the cost. If you are suggesting in a project a very good low carbon material which is disturbing the cost of the project, there is no taker for that particular material. So you need to see that if that material is not hampering the cost of the project, one. Second, as I am saying that today I am developing a low carbon material and taking a design period of 60 years. So I have to see. Earlier it was not seen that what will happen to concrete when the life of the structure exhausts. So we are looking into it right now. But if we are into the sustainable construction era, then we are supposed to look into that if I am developing a certain material, what will happen to it once the design life is over. So I am supposed to look into the circularity. These indicators are broadly discussed by us in 2-3 days. But I just go through that if I am choosing a raw material, I must go for renewability of the source. If I am going into production phase, I must go for energy efficient process if it is possible. For example, I come from the in situ conventional concrete, I have upgraded to the ready mix concrete, which is reducing the wastage over the site. Then I have upgraded to the precast concrete. Then I have upgraded to the modular in situ. Then I have upgraded to 3D printing. But I have to look, this is the technology advancement. Is it really advancing in CO2 emission reduction? That I have to calculate. Many of you will be calculating, taking up one material at a time, case study, and doing your own research on that. Then it comes to the usage phase. I have already discussed about it, that energy efficiency of the building and recycling phase. Reusability in new material production. Waste which is coming out of the construction. I want to put here 2 different concepts. If I go to the second phase, production phase, and the recycling phase, there are waste being generated by construction industry in 2 ways. One, when the construction is taking place. So if you quantify the material which is required for you, if your BOQ is very estimated thing, or I mean it is not the accurate one, then probably you are wasting the resources over there, not only putting an impact on the CO2 emission, but putting an impact on the cost as well. Second, when the life of the building is over and the building is being demolished, what is happening to that particular waste? That is the another waste. So new construction waste generation and the construction and demolition waste generation. Both the things will be there. Okay, so come to the last point, which I told that I have to choose a material which interacts nicely with the building or the environment. So this is a 3-stage diagram we can see. The first stage, there are 5 indicators for low carbon materials. Just now I discussed them. Renewable source, process efficiency, design at the atomic stage, waste utilization, and recycle content. Right? Design at the atomic stage means you have a conventional material, you add on something maybe on a scale of nano to it, and then you make a good performing material. For example, you have construction demolition waste, you dope some nano material into it, say nanosilica you are doping into it, and then increasing the strength of that particular material, which will be at par the conventional aggregate, and you can use it. So that is how you have reduced the utilization content or quantum of the natural aggregate. In turn, you are saving it, reducing the carbon emission. So everything out of this particular figure will depict some stage in the low carbon material development, right? Then it comes to low carbon production. For a low carbon production, first thing what we can do is we can increase the durability. If we increase the durability, how does it reduce the life cycle carbon emission? Is the denominator is going to increase. If we use a certain material for 10 years, the denominator is 10. If I use the certain material or the entity for 20 years, naturally, yes, the denominator has increased. When the denominator is increasing, the indicator is going to reduce. Then I go for environmental interaction, design flexibility, and modular management. So in modular, this I think I have discussed in the last slide. Last comes to low carbon services. So BIM, which gives you a correct idea of how much resources you require at what particular point. If you include the project management with the BIM, not only building information modeling, but 4D you are including that time with it, right? Then comes the digital tool. Then the supply chain, because low carbon potential or GWP potential of material totally depends on where the structure is taking place and from where you are fetching the material. So transportation energy sometimes becomes very crucial. Say for example, if you are making a bamboo fiber reinforced panels and you say because it contains bamboo, my material is a low carbon material. And just imagine that you are procuring bamboo from 300 kilometers. Because it will be a lightweight material, the transportation emission will be greater than the truck will not completely be loaded to its fullest capacity. So you are losing there, right? So supply chain also is a very important point in that. That is why the sustainable material, the first definition comes is use locally available things. And then comes the lean construction. So in lean construction, the basic focus will be on reducing the waste in the construction activity by set-based design. So in continuation to that, we can have a strategy. I can fix a GHG emission target for my own material. From where is it coming? GWP. From where the GWP is coming? If I want to compare my own material to certain EPD which is established in some different location, I want to match my material to that and I want to design my material accordingly. I have a target. I design the specification. Then I design the baseline target for functional performance because that has to be satisfied. Then I go for material calculation of embodied carbon emission for all the constituents because I have designed the specification. I take the embodied carbon emission for each of the material based on the composition, proportion, I calculate for my unit. Then I go for material quantity estimation and then I review it. Then I add into the manufacturing, fabrication, product, assembly CO2 into it. And then I calculate the total embodied CO2 emission for the developed unit. For concrete, we are calculating it in per cubic meter. Correct? but it will be different for same grade of concrete if it is in the shape of panel. It will be different for the same grade of concrete if it is in situ beam and column. So that much minute detailing we are nowhere you will see in the calculators we are doing. But if I am using it, the thing, I am developing the material, say in a form of a unit which I can directly supply, then I have to go for that particular unit. It changes because the formwork required for the panel is different than the formwork required for the column. And if I am adding that processing CO2, the values will change. Then I come and see if it is complying with the performance target. If it is complying, then yes, test the prototype, go for the commercialization. Material quantity estimation, or if it is not complying, go for identification. Energy intensive material. So if you find that my unit is not complying because I have cement as a constituent in the material, target that. Target that. Identify the low embodied carbon alternatives for that particular material. Bring in it. Again, do the testing, technical marketing feasibility. Go for, if there are more than one or two alternatives, go for the multi-criteria decision making and check the feasibility and come into the same channel again and commercialize it. This is a strategy for low carbon material development. It is not as simple as it is looking on the screen. Because the trap will be when you identify the non-complying material. Sometimes the non-complying material is the essential material for functional performance. I am using a polyurethane insulation. So I am using a polyurethane insulation. Polyurethane, if I say it is a non-complying material, increasing the GWP potential, then what happens is insulation is because of that. Not because of the cover sheets which I am using for making those boards. Correct? So if the scenario is like that, then there will be a trap. If there are alternatives, different alternatives, then there will be a trap that how I am going to decide which alternative is feasible for me. Okay, let us quickly go through the evolution of building blocks, how they have evolved. Low carbon building blocks, how they have evolved is, they evolved in two ways. One is the material evolution has happened and the technology. You remember the first slide which I told you is availability, then durability, then strength, and then likewise it has happened. If you see, you can relate it to it. So materials you wanted to have in cement binders, but you wanted to reduce cement binder. So what did you do is, you changed the cement binder, you added something into it, and then you came up with the, or you made the block with less cement, lighter material, so that the total potential or the building potential, if you use it in a building, the total potential of the building will reduce. The CO2 emission potential will reduce. Or if you are going for cementless, you have n number of options: compressed earth block, then flash, lime gypsum block, and so on and so forth. There are many. What happens is, if I'm using industrial waste, I outrightly declare that because I'm using an industrial waste, my material is a low carbon material. Right? But then I have to go for the flow chart, which I have seen, that I have to do an analysis that is it really the low carbon material. Then comes to the technology. Either you go with an manual compaction, then you go with the hydraulic compaction, vibratory compaction, the energy will change, and then the blocks evolve. There are certain 2 or 3 things which we worked into. So you say that if I'm using an industrial waste, my material has become a low carbon material if industry does not find a suitable place to dispose of that material. Now, when industry is trying to dispose of that material, what the industry is going to do is, when they are dumping the material, they will be using land. So the land use instantaneously changes. The land which can be used for growing vegetation, for sequestration of CO2, has now changed into the brown field, and it is not helping anything into the CO2 emission reduction. Right? So foundry waste you can see at the top. Then you can see there are different waste which Raliga sir's team has developed. Basically, I have taken this thing. recycled paper, pulp mill waste, sugarcane garbage waste, construction demolition waste. So everything was going into dump which has been used and made some building block, and then the CO2 emission has reduced. Now, here comes the second point is, are we using the waste as it is within the form which industry is dumping? For example, slag. So you are aware that there are two forms of slag which we can use. One is the slag aggregate, crystalline form, and another is the granulated form. So for granulation, you require some particular system. So is this system CO2 friendly, or I am putting some more energy into it? So if it is energy intensive, that particular energy component I have to put, right? You want to ask something out of this? If there is a question, you can simply interrupt. What I have done is I have put all the information which we have into the nutshell to have a clear picture of what low carbon material. As I said in starting, that I am not suggesting that please use this material by this company, this is a low carbon material, or developed by me. Is use your conscience to decide that whether this material is low carbon. Evolution of concrete, which has not stopped yet. Let's continue. Concrete in material, microstructure, and the technology. Three things. So in material, how concrete has evolved? That we are using blended cement. Now when it comes to blended cement, we are aware that our standards do not allow us to use more than 5% of clinker blending. Right? Why do not they allow us? Is because the performance of that particular material probably will get disturbed. So if we are trying to achieve one particular criteria, the another criteria may get disturbed. Then supplementary cementitious material. So they say that if I am using fly ash, instantaneously my concrete becomes low carbon concrete. Not always so. And if I am using a good quality of supplementary cementitious material, it does require some processing energy to bring it into the current form, which can be compatible with the cement. So supplementary cementitious material. Then I have the alternative binders. For example, here alternative binders are alkali activators, magnesium-based binders, bio-based binders, and polymer-based binders. Or somewhere it is plastic waste as well. Right, liquidified plastic waste which can be used as a binder. Basically, it will be a polymer-based binder. Then we use microstructural properties of concrete to reduce the total CO2 emission potential of concrete. How is this possible? When I change the microstructure of concrete, the strength of concrete changes. If the strength of concrete changes and I can achieve a high performance or high strength concrete with that, the total quantity which I will require for similar case changes. If I'm changing or reducing the quantity for the similar case, and per unit if I compare, then the CO2 emission potential of that particular component changes. So even though if I'm not adding anything from the waste, but simply if I'm changing the microstructural properties of concrete for high strength, then also it can make my concrete as a low carbon material. So there are some methods. You use particle packing theory, you use nanomaterial doping as I already suggested. Then you use the carbonation of concrete component or concrete aggregate. You do the carbonation, then the strength to some extent, and then there is the bacterial concrete as well. Right? Then you change the technology. You change the technology of producing the cement, where you replace the cement, the fuel which you are using, the coal which you are using to make cement by alternative fuel, say biobriquettes or waste rubber tires or etc. Like that, what industry is using right now. Then use the advanced manufacturing technology. Probably this all we have discussed. That 3D printing may be there, precast, prefabricated, modular construction may be there. So cut down the wastage in the design. And there is a totally different domain of discussion. How you can cut down the waste while doing a proper designing, right? I hope you will be able to join all the blocks of last few lectures when you think of as a in the holistic manner towards you will have an approach towards the low carbon materials. Okay, this is CNT generation. This I'll skip. Demolition is a modern problem In our country, it has a very wide range. You will find that the older buildings are being demolished manually. The bigger buildings are being demolished mechanically. 2 bigger buildings are being demolished by blasting. We all know the case studies which we have heard of. How the demolition is adding into CO2 emission? Or if I take the WLCA for the building, how is it adding? So cradle to grave, then again you come into it, right? How is it adding? If you do it manually also, you have to dispose of that material, the method which you are using to dispose of. If you do it mechanically, what mechanical facility you are using? If it is off-site disposal, on-site reuse, for on-site reuse, what mechanical facility you are using? And if you are recycling also, how much is the recycling potential of that particular material? What methods we are using to recycling? Are we using that material into low grade recycling where it does not give us much age over the CO2 emission in our new building material? So this is how we can trace the demolition phase CO2. Stage 1, stage 2, stage 3, as I just told you. Stage 1 is the method of demolition. Stage 2 is the machine which you are employing. Stage 3 is the how we are sorting that particular demolition. Let us make it clear that here when I am talking about demolition phase CO2, I am not talking about the components, complete components of the building. I am only talking about the masonry and the concrete which is coming out of the building. Or the ceramic material, probably the tiles, the masonry and the concrete which is coming out of it. I am not talking about the doors, windows, roofing sheet, the plumbing materials, etc. There is a completely different area for a different treatment is required, because you know when a building will be demolished, 2-3 things will come out. Something which you will be able to sell, something which you will be able to reuse, and something which you will have to dispose of, or you will be able to recycle. 10 years ago, they were saying that the concrete is a non-recyclable material. Now they say that the concrete is a completely recyclable material, right? So that shift we have got in 10-15 years. Okay, this is methodology, data collection. This is this is a particular calculation we have done for one case study. If it runs, let us see if you can see it. Is it visible? So to understand that carbon emission through the demolition activity, this is a small Excel-based tool. Some background info about the demolition, how it's going to do, what we are going to do in this particular tool. Then the demographic have to be put by the user in this particular sheet. Then there are 3 options we have taken. One is the complete manual demolition, then mechanical demolition, and the hybrid. Machinery, the fuel consumption coming out of it, and indirect is the movement or the transportation of that machinery to the site. So if it is going into the landfill, the distance which that particular hauler is covering up to and fro. If it is being done on site, there are different types of equipment you are supposed to use, say bucket pressure and all, which will give you the aggregate in 50 mm size. So bucket pressure and all, that how we are going to use that. And then if it is going to a centralized recycled concrete recycling plant, because Nagpur has one plant. Recently, 2 years ago, they have started one recycling plant here in the Nagpur, where they are doing the recycling of concrete, collecting it from all over the city and recycling it and selling it for reuse. And then you decide to get the carbon emission kg CO2 equivalent because the factors of multipliers, C1, C2 is I was saying that factors we have used for equivalent only. So equivalent, and accordingly you do the decision which particular you are supposed to use. Okay. So this I close. I think we are back in the meeting. Yes. Is it visible? So these are the results which I have shown in that particular Excel toolkit to you. And it says that if you do into actual demolition, indirect transportation, waste disposal has a very larger impact on that particular CO2 emission which is coming out of the disposal activity. Then if you recycle the material into a certain material, then also you can offset the CO2 emission which is coming out of the demolition activity. So this is a small example of one block prepared. First, it has to pass through the target performance targets which the block has to perform. If it is passing through, then you can calculate how much emission. So using on-site recycling, basically what did we do in this is, there was a case study we took in BIM. We prepared a model. I mean, the students who worked on this prepared a model. They calculated a total concrete coming out of that particular building. How many blocks can be prepared out of that concrete on the site? And then how much of that stuff the building itself can reuse, because there will be no transportation in that particular case. And how much can be sent into the commercial use. So the calculation was that the cost also reduces and the carbon emission reduces to a extent of 3 to 12%. If I use that particular material as it is, the replacement percentage will be lesser. But if I give some processing energy to the material, so as soon as I say I give some processing energy to the material, it will increase the CO2 emission associated to the material. But can it offset by increasing the replacement percentage? So if I'm not treating that RCA or recycled concrete aggregate, my replacement percentage probably will be 10-15%, which is suggested by Indian code. But if I treat that RCA, there are several methods you can see on the screen. So if I treat the RCA, probably the percentage will be increased up to 50-60%. And that increment in the replacement percentage will offset the CO2 emission which I have used or which I have emitted in the processing of that material, right? So again, there is an example of this treatment method, how we are selecting it, how we are doing it, and what is the impact. I think this is a complete different perspective. I just wanted to show that yes, if we do it, it can happen like that. Then from the material, we come to the building. So again, there is a concept of I have several stakeholders in a building. The left column of the sheet, you can see that there are different stakeholders. And if I am looking into the operational energy in the construction phase, also I can reduce the operational energy if I target these particular stakeholders. So there are broadly taken as construction engineer, electrical consultant, plumbing consultant, energy consultant, geotechnical, and landscape consultant. Again, there is a small tool which has been, and this is the methodology or philosophy of that particular tool. And two cases are defined. One is the base case, one is the best case. This works on the same concept as we have, just looking at EC3. You have the carbon emission factor. For each of the consultant, you pick into. I think that hyperlink is not visible to me here. I'll show you that too. Once I stop sharing it, it is there in the folder. So base case and best case design conventional option has been selected, and the carbon minus or carbon efficient option has been selected. And in total, the reduction in the carbon emission has been calculated for a complete building case study. Yes. So, I mean, it looks like a typical construction engineer sheet. So in this construction engineer sheet, you have some data which you input into the sheet. Then you have some options which you can select. So a base case options and the best case options you can select. Only 2-3 options have taken, but there will be a number of 50-60 materials we have. All 50-60 materials we cannot use for decision making in a certain building. So we have to decide what is the major impact making material that only we are going to take into the decision making, right? So there are major impact making materials, say cement, blocks and steel. If we select and the best case we select, then we go into the decision making. So these are the results. Once the result is there, if I'm selecting a certain material, I have to see what effect it is going to put on the cost of that particular project. So there are two indexes we have calculated here. One is the energy cost index, another one is the emission cost index. I mean, for 1 unit cost, how much energy I can reduce and how much emission I can reduce. I have to decide that whether budget is my constraint or that emission is my constraint. This scenario comes when I want to take my building to certain certification. You must have heard of certification, right? Rating systems. So if I want to take my building to certain certification, probably in that case, the budget will not be a criteria for me, but the emission or embodied energy will be a criteria for me. So this gives me an idea how can I select the particular material based on this index. Okay, I hope this is clear. So probably you will be able to select a low carbon material for your own project, right? Now I have 3-4 options. Which to select? How to make a decision? As I told you in the start of the session, I'm not going to give any example of a low carbon material because no material is truly low carbon for my own case. I have to choose it for my own case, correct? Decision making methods can influence decisions outcomes. Yes or no? So decision making methods, which particular method you are choosing can certainly influence the decision outcome. In this case, what should be the decision outcome for me? How much GWP I have reduced for that particular component or particular material or building, right? People's decision trigger actions. Action cause outcomes. Outcome matters. And decision matters. What is the baseline? Is you have to have at least 2 things in your mind while making a decision. First and foremost thing in my mind will be the cost. Another will be the material advantage which I will be getting. Right? So there is a method, we'll see it. There is a method which is called as choosing by advantages. Those who are following lean philosophy probably will be aware of this or may have heard this particular term. It's called as choosing by advantages of CBA, which helps you confusion to decision. You are happy that you have done. It is a systematic approach of and practical advice for decision makers. What I am showing here is the 3rd step of CBA. If you really want to pursue CBA, you can go for this book by Jim Sir, who has initiated this particular method, choosing by advantage decision making system. And there are instant CBA, two-list CBA. First practice instant CBA, two-list CBA, and then go for this tabular method. I am showing you tabular method over here. So it integrates multiple perspectives, identify relevant sustainability factors, makes transparent trade-offs, documents the rationale. See, the catch is today you are building a certain structure. After 10 years, some different consumer comes in and they ask, who decided this material? And then you say, the project manager at that time decided this material. How come you say that this is a low carbon material? So at that point of time, there should be a certain documentation which can justify your answer. That yes, at that time, the project manager calculated this thing and this is the justification by which we have selected this material or they selected this material, right? And this completely separates value from the cost. The dilemma of a material developer will always between a value and the cost. So this completely separates 2 things, value and the cost. You have to decide which you value most, value or cost. Okay, so let us see the terminology. I know we are running out of the time, but I'll take some 5-6 more minutes to complete this. It's an interesting one, so you must go through it. Terminology says that alternatives. there should be 2 or more things that you are choosing between. Be as specific as possible. You cannot say any block will do, right? You should tell, I have choice, AAC block or Ramdell block. You have to give specific choices. You cannot say any block. Factor. This is an element or part or component of a decision that you are considering. For example, you are considering the factor of weight of the block because you want to make the masonry in your building as a lightweight. Nowadays, masonry is only being used as a say partition or a facade like thing. So you want to make it a lightweight. So you'll say factor is weight. Criteria. So there is a factor and there is a criteria. So there are some guidelines or specification, there are some mandatory guidelines. Those who have seen the green building rating system will understand that there are some mandatory criteria and there are some desirable criteria. So prescriptive and descriptive. So the mandatory criteria you have to tell and the desirable. For example, in the block, IS code says that the minimum strength of the block for a non-load bearing type of thing should be 3.5 MPa. If it is lowest class, it is used in the partition and all. So this is a mandatory criteria. Now a block being lighter or beautiful is a desirable criteria, right? Or insulating is a desirable criteria. Then you have the attribute. For each of the block, you will have certain characteristic or attribute according to the criteria. And then you say the advantage. And the due course, I told you 2-3 things. I told you weight, I told you insulation, and I told you strength. Which is most important for me? Naturally, strength is more important for me. So on a scale of 1 to 100, I'll say it is 100. Importance of this advantage is 100 to me. Then I say the insulation. It is equally important because the block I'm using as a facade material. So it is, but it is 80% important. So it is 80. Right? And then I say the weight. Lighter. I can say it is 30, 32, 35. Whatever it may be. So that has to be. Now you will see, CBA cannot be done by a singular person. Isn't it? Because then many people will be involved in that. So this is basically a part of a collaborative project management. Many people or all the stakeholders involved are supposed to sit. Goes in the same way, steps. Let us see the step directly. So I'll take the example. 2-3 more minutes. This is an example of a global IT company seeking the LEED Gold certification for its international office. So before I start, I must cite the acknowledgement of Paz Oreo. This is their paper, which I have an exam from which I have taken the example. You can see this paper. This is available on the Google. So the project scope is they're selecting the ceiling tiles, which are your false ceiling, which we call it. It has and for cost and sustainability. Okay. So scope is they want to renovate multiple global offices location using a consistent design approach. I'll share this to you. Renovation of multiple global office location using a consistent design approach means they don't want to change much of the design. So their ceiling tiles should look alike because you see, if there is a chain of hotels, everywhere the interior is same. So they want to keep that way. And they want to achieve the LEED Gold certification. Naturally, carbon emission equivalent will be a major criteria for this gold certification. The design strategy is they have a San Francisco office that will serve as a prototype design, and they have representative cities analyzed as San Francisco, New York, Sydney, Dublin, and Tokyo. The procurement method is contractor will design, build everything, right? And focus of the study, cost and availability of ceiling tile, probably from one manufacturer, because if you order bulk, probably you will get discounts on that. And regional product availability and logistics also can be a key consideration. Okay. So now there are different alternatives. So these are the design goal and objective which are narrated. These are alternative available with them. So their team did a survey in the market. They took some alternatives. There are 4 alternatives. One is Optima. This is a brand name. Then Ultima. Then Optima PB and Optra. The Optima has a material glass, material as a fiber glass. Ultima is a mineral fiber. Optima is mineral fiber glass with plant-based binder, and Optra has a biosoluble glass wood. Constituents are different, so their response to the environment will be different. You see, there are some bio-based material also. There are different manufacturing location. Manufacturing location is changed. It means the transportation CO2 is going to change, right? Aesthetically, all options look the same. You can choose any. All are supposed to be installed with the same system, so there is no variation, and the sizes are also same. So they come up with certain factors. There are general factors you can see to the left on the screen. We cannot choose options based on too many factors. It becomes confusing. So what we do is, what they did is, they selected certain important factors which was there for ceiling tile, and they called it as a relevant factor. So the relevant factor which they selected was acoustics, antimicrobial, so there should not be any microbe growth on the ceiling tile because it's an interior material. Then durability has to be there, weight, because if it is light, it will take lesser weight on the system. Insulation value has to be there, VOC, because it is inside being used. Then global warming potential of that particular, because they are supposed to go into the LEED certification. As soon as you delete this criteria of LEED Gold certification, your choice method completely changes. So how to do the CBA is tabular CBA. You prepare a table. I am showing only one factor, and then I go to the table directly. Factor and criteria. These are two different things. Okay, look at it carefully. Factors and criteria, these are two completely different things. They are not used interchangeably. We should not confuse between them. Factor of selection is acoustics. See, in the previous slide, we selected some factors. So factor of selection is acoustics. Acoustics is exhibited in form of NRC. NRC is noise reduction coefficient. Criteria is higher the noise reduction coefficient, it is better because it is going to work great in acoustics. So I have four alternatives: Optima, Ultima, Optima PB, and Optra. Alternative 1, 2, 3, and 4. Attributes are for each of that. So alternative 1 is Optima. Attribute is it has NRC 0.9. NRC is always less than 1. So NRC is 0.9. Second alternative has NRC 0.7. So instantaneously you say, okay, this is 0.7, this is 0.9. 0.9 is very good for me. Because your criteria is higher is better. Right? So what we have done in the third row is, we have calculated what is the shift or delta advantage available to us. So delta, for calculating the delta advantage available to us, we are comparing only two at a time. Two alternatives at a time. If you look at the screen, you will understand that the lowest attribute taking alternative I have taken as important 0. Right? And then I have calculated the delta based on that. 0.9 minus 0.7 is 0.2. And because it is a ceiling tile, the acoustics holds 100 importance of advantage on a scale of 0 to 100. Is that clear? How we have done it? Now there may be a confusion that in the third one, Optima PB I have taken as 0.25. But still I have taken as 100. Why not 100, 500, 10? Why only 100? Because the scale essentially is 0 to 100. And I know that if it is 0.9 or if it is 0.95, that does not make much difference. 0.7 to 0.9, it makes difference. So in my case, if there is a different material and if it instantaneously changes classes, I mean strength 3.5 MPa, strength 3.8 MPa does not make much difference. But strength 3.5 MPa, strength 5 MPa, yes, it makes a difference. So that difference I am going to take care of here, right? We'll see to all of the factors: acoustics, antimicrobial, durability, weight, insulation value, VOC, and warranty. So all importance of advantages IMP 15, 25, 50, 45, 0, 90 in the column for Optima fiberglass. Similarly, for other methods, I have taken all this importance of advantage in abbreviated, we call it as I of A. So I of A I calculated. Now what happens is CO2 emissions I have to calculate it based on where this tile is being manufactured or where the tile will be used. Correct? So if the tile is available commercially in San Francisco and being used in San Francisco, transportation will be lesser. So the CO2 emission potential will be lesser. So this matrix, you can see the serial number is 8 only for everything because the factor is same. Only the value is different. Values are different because the transportation distance is different. That is why CO2 emission is different. And then in the lower table, 355, 205, 445, these values suggest the summation of importance of advantages. What is the largest value here? Is 450. Right? So the tile which has 450 importance of advantage is the most advantageous for me. Isn't it? So can I select it? So the other parameter comes into the picture. How much does it cost? Right? Shall I settle it for any budget? So then what I do is I draw or plot the values of IOF with respect to the cost taken on the horizontal axis, IOF taken on the vertical axis, and we plot the values for different alternatives or importance of advantage. You will say there were only 4 alternatives. Why there are so many points on the graph? There are only 4 alternatives. Why there are so many points on the graph? So if you read that point carefully, you will find the right topmost I am going to read is Optima PB Sydney. Optima PB in scenario, if you use it for the Sydney office, it gives you importance of advantage 450, but it costs you per unit $6. Right? Now it is up to all stakeholders sit and decide which particular I am going to choose in what scenario, because I have taken into consideration low carbon. So we can read this graph in 2 ways. We can read it keeping the brand or the alternative same. So if I keep Optra same, I can see Optra Dublin, I can see Optra Tokyo, I can see Optra Sydney. They are same, very less difference in the cost and same advantage, importance of advantage. So I can choose this particular material for these 3 locations, right? If I see Optra in different say scenarios, then probably if I am going for lesser importance of advantage and settling down, then the cost is also less. If I choose the location, you can see Optima PB Sydney different, Optima Sydney different, Ultima Sydney different, and Optra Sydney different, out of which Optima PB and Optima are giving high importance of advantage at a higher cost, whereas the Ultima and Optra are giving lower importance of advantage at a lower cost. So that I am supposed to decide which I value the most. I hope it is clear to you. This method is not as simple as it is looking, because there has to be too much of brainstorming on selection of alternatives and the importance of advantages. Okay, I am eating your eating time, so I will stop here. So summary is, we looked into the interaction of low carbon materials and services. I hope I was able to clear off the fog in selection. Then design strategies for low carbon material development. So probably when you will go into developing some low carbon material, you will keep in the mind the flowchart. Then you have to choose the material after doing WLCA, and you have to choose wisely. There are many MCDM available out there. I wanted to put a different method for you. So I think that is all from my side. Thank you. So if you want to ask something, we'll have just 1 or 2 minutes, or otherwise we'll stop over here. For those who are present in the hall, I am already there, so we can discuss. Those who are virtually present, if they want to ask something, I'll take up, or I'm always in the VNIT. You can talk to me anytime. Okay, so we'll stop here. We'll move for the lunch now, and after lunch,